So I have a few questions which come from this row operations. So in row operations, you define three operations, right? So there was three kind of operation, maybe O1, O2, O3. So can you say if you find like any of it redundant, any three of it, among the three, do you find any one of them redundant?
Redundant is repeating, right? Repeating.
Uh, Repeating in the sense that, yeah, it can be done with using the other two.
I mean, you're saying unnecessary? Okay.
Yes, unnecessary. It was in the other order. Let's keep the order as it was.
So the first two are obviously not unnecessary, like they are required, but the last one, swapping of the rows, I'm thinking that can we like obtain this swapping through operation number two?
Yes. Let's see. You may need two other you may need both one and two.
Yeah.
So suppose you replace this by Ri plus Rj. So, no, so we have Ri.
No, so my question is that okay, so like if we consider every row as a vector, okay,
Yes, every row has a vector, right?
then we'll get okay, so so we have now our job is to swap Ri and Rj. So in the place of Ri we get Rj, and in the place of Rj we get Ri. So
Right.
if we can obtain Ri as a linear combination of any two vectors, okay. So
Hmm.
now here I am treating the vectors as rows.
Hmm. Right,
Each vector
as
as a
rows.
row.
Hmm.
So if I can, so in those among those vectors, if I can obtain Ri as a linear combination and also Rj as a linear combination, then I think we can swap those things using operations one and two.
Right. Yeah, you will need some. Yeah, I understand. Some kind of combination.
So like yeah, wait, but we know that if we can like find a linear combination
Hmm.
of that vector, then can we say like so if we can, so now we'll not treat them as vectors, let's say we'll treat them as like the way we treat the system and the linear equations, okay. So if we can get one linear equation through a linear combination of a system of equations, then we can say that and also vice versa, then we can say that they have the same solutions, right?
Yes, that's right.
So and here so basically this column, R column, if it has the same solution as, or sorry, this row, Ri, if it has the same solutions as
Hmm.
all the other rows, uh, but then all the other rows must have also the same solution as Ri. So no, we cannot use that both the sides.
Hmm. Okay.
So we cannot
Yeah,
use that
that argument seems. Yeah, I understand.
because it
Something.
should happen both ways.
Yes, then
Yeah.
only you can. Yeah,
Yes.
something very simple will work. I just maybe. Yeah. Just so this is like a exercise. Like I'll say what I got. So I say I'll make this minus Ri. Then I will add this row, jth row to ith row. I will get this. Then I will add minus of this to the jth row, and I will get this. This will be I. And then I will add this to this, and this will be gone. And it will be swapped.
Yes.
So it's a,
So the,
and it's just a, yeah, small thing.
so this swapping is unnecessary. Like
Is
this,
redundant, yes. But still, I mean, there must be some wisdom in keeping it, which I don't know. Why?
maybe like this is like bit non-trivial, right? The way we have swapped it using operations one and two. But this is
No,
like
no,
just
I don't think it's non. Okay, yeah, those are just words. Yeah, maybe it's just elegant to
non-trivial.
keep it. Yeah, maybe it
Like
makes it
you
elegant.
have, yeah, it's like similar to this thing, right? When you have a four-wheeler which has a gearbox and a four-wheeler which has automatic, you have this automatic function in RI swapping, but you can obviously drive even with the geared thing, right? But it is much difficult to drive.
Yes, this is much more, yeah, much more convenient to know that you can just swap. Yeah, and the swapping is important, right? Like in the last time we were doing because there is something called row reduced form, and I think there is a row reduced echelon form.
Yeah, yeah, that is the next thing which I'm going to
Yes, so there that's basically the same thing, but only that the zero rows you just put them right at the bottom. Okay, and you just make sure that the pivots appear in the uh, sort of like this. So, for example, you don't want something like this where you have a zero row and then a pivot coming here.
Yes.
Yeah, so you just arrange the pivots in a decreasing order from right to left as you go down. And to do those things, you need this swapping. I mean, to do them
Right.
elegantly. Yeah. Otherwise, so here, but I would like to just check one thing is that we know that O1 plus O2 imply O3, right? So it's like if you treat O1, O2, and O3 as vectors, right? Then O3 sort of depends on O1 and O2,
Okay.
right? It just is toying around with it, and but is the converse also true? Like can using O1 can you replace O1 by using O3 and O2?
Not always.
Okay, can you give an
Because
example?
I think like I know when I can like when O1 and O2 becomes similar, when we have got a row of 0 0 0 0 0, O1 O2 becomes similar operations.
Right.
Like O1 can be we can get operation O1 from O2. Yeah. But
Mhm.
I don't think that O2 using O2 and O3 we can get O1.
So can we give a small proof? Maybe we have a matrix like this, and um you want something like this, right? This is applying O1 multiplying by 2.
Yeah.
Can you prove that using other two you cannot get to this matrix B? Let's try to prove it, right? It will be interesting if you can prove something like this where you cannot get to somewhere. Right? So you understand the statement because this is slightly vague, right?
I understood what you're
Uh,
saying. Like we have like if the proof like I think it has to we have to use some contradictory argument because
yes, because we have,
direct
yeah, because we don't
proof.
have to, yeah, because there is nothing to prove. We have to disprove something, sort of.
Yeah.
So there is something which is, see, if you apply the operations, maybe you will see that there is something which doesn't change in A when you apply O2 and O3.
See the strength of O2 is like really good. But
Okay.
O3 I just cannot understand like what is its uh,
Right. O3 is just the swapping, and it can actually
like
be
I'm just
gotten from O1.
focusing like can we just like never get O1 from O2?
From O2 only.
Yeah,
So you can, that will be easier thing to prove, right? That
yeah, that
only
is what
applying
I'm trying.
O2s, any number of O2s you want, you can never get to B, and you cannot get, because there is something fundamental in O1 which is sort of scaling a row by a, it's increasing the strength of the rows in a way, which you can say that O2 is also doing.
Yeah, but like if geometrically, if you are saying it's also like shifting some angles, right? O2. And O1 is just like dealing with the length.
Yes. So let's see it geometrically then what happens.
That is what I'm saying. That if we have got a zero vector, then we can get O1 from O2.
Yes, yes, yeah. If it's zero vector, yeah, then the, so like if you have this, then O1 can increase the area. But if you apply O2, then as you're saying, the angles, if you apply O2, then what happens? say that 2 times this. So this is V2. So what I mean, let me write it clearly. This is V1, this is V2. Or actually R1, R2 only, right? So let's say 2 times R2 I do. Then I have to add it with R1. So it comes here. Yeah, this picture is not too good. But you see, it seems like the area of the parallelogram doesn't increase, right? I mean, one can see it like this. So I'll try to explain it in this way. I'm trying to say that when you apply O2, as you were saying, like it is increasing the length, but it is also changing the angle. So overall, it doesn't increase. It doesn't increase anything. Like if you have R2, you can do 100 times R2. So you can go very, very far. Okay, you can do, let's say 10 times R2. So you get here. Right. And then this will come here, the summation. R1 plus 10 times R2. Right? But then R1 plus.
So including the swapping, like I am, if we are considering 2 times, so my point is that let's say I've got M, N, and L, all right.
Mhm.
Now we have done this first operation of O1 is this that I just multiply the first column by L, all right, first row by L.
Hmm.
So if I can have two reals, sorry, two numbers in the field f m comma n such that m r1 plus n r2 equals L R which thing M R1 plus L R2 equals L R1.
Okay.
Then obviously I can like derive O1 from O2 and O3, right?
Oh, so this R1 is not that R1. This is just that. This R1
O1.
is that R1. Yeah.
Yeah, capital R1s.
Um, so you're saying
Because
that, yes, yes.
because O2 is like if we just write O2 and if we don't like add it, if we just write the terms of O2 repeatedly, if we do it, then it will look some like it will somehow look of the form MR1 plus NR2, right? And even if we swap and then again perform O2, then also we will get something M times R1 plus N times R2. That is for sure. So if all of these operations, if
Hmm.
if this exists, then obviously we can derive O2 and O3 from sorry O2 from O2 and O3 we can derive O1. But now I think we should get a condition that there will exist a zero vector here from this thing. Like one row has to be zero.
Uh, no, so the L is fixed, you're saying.
Yeah, L is fixed, right? L is basically the two which you have done here
Right. Yes.
in that
Yes,
diagram.
yes, yeah. But then such a M and N you're saying may not exist.
Yes, and if it exists, then at least R1 or R2 have one of the rows has to be complete zero vector.
No, no, it doesn't have to be complete zero, I think, but it will not exist in general. Like saying that it has to be 0,
Yeah.
that's too much, but it will not exist in general. And that I think you can just see, because like then it has to be like this,
Hmm.
right? And then there are some, then you'll get some divisibility conditions and so on, right? Which doesn't have to be satisfied,
Right.
because this is a vector, right? It's not a number. So then you can derive some conditions, but you can see that in general it is not possible.
Yes.
And what I was saying is that also, that as you can see, that when you do O2, then you really don't increase the area of the parallelogram. Okay.
Hmm.
If you stretch, if you can already see it, otherwise try to stretch your imagination. You can, maybe I should also try to just understand it clearly, because I know it as a fact, but just to try to see it, let me just try to see if I can do it. So I do this R1 plus 10 times R2. Okay. And now we want to add these two vectors, R1 and R1 plus 10 times R2. So can you roughly explain where this will land?
See?
So we want to take the parallelogram completed by these two vectors, right? This
Ah.
vector and this vector. So
Ah.
where will this be?
Uh, yeah, you have to draw the diagonal.
Right. So this is this, and then you draw the diagonal. It comes like this, right? So you see this area. Now, can you argue that this area is the same as this area that we had initially? That seems a little, yeah. Or we don't
No,
even
no.
need the
Or,
parallelogram.
or, no, you're doing the thing. Basically, you're no, but actually,
Yeah, basically this triangle and this triangle, they
they
should
have
have
the
the
same,
same area.
perhaps common side lemma
Uh, no, the side is common,
contained between the same parallels.
but they are not parallel. Yes. But you
No,
can
they
somehow prove it.
are they
Uh,
not?
which ones
So
are
if you
parallel?
connect R2 and R1, that black point, R2 and black point of R2
Uh,
and that black point.
right.
So what can we say about that segment, about that vector? Mm, it's obviously not parallel to R1, right?
Yeah, it's not parallel. It's R1 plus 9 R2, so on.
So
No, so
then
you
how can
can
we
you can prove this. It should not be difficult. I have proved this in my uh, free time or something, at, at more than once in my life. You can try to prove this, that this area will not change. Okay.
okay.
Somehow it's a, maybe try to find an interesting way to do this. Next time you can tell us. Okay. That this area will not change. So see, all I'm trying to say is that when you have this R1 and R2, this, and when you replace this by, let's say, 10 R1 plus R2, right? Then the determinant of these two things is the same.
Mm-hmm.
Okay. And the determinant is basically the area of the parallelogram. Okay? That, that's the cross product. That is, yeah, from any angle, or you can just prove that the determinant is the area of the parallelogram. Okay, you can explicitly prove with sine theta, cos theta, and so on. Okay. And that is the problem with B, the determinant is different, right? This operation changes the determinant, and
Yeah.
the other two don't. I mean, the last one just changes the determinant sign by -1.
Yeah.
Then that's a fundamental invariant.
Right.
Okay, that is a fundamental invariant. And even there was one problem in test of mathematics which was based on this. I don't remember what was the problem, but there is one of the operations, it doesn't change the determinant, other two don't change. But maybe try to prove this next time. This will be an interesting like basically with this interpretation you can try to prove like try to explain why area behaves the way determinant behaves. Maybe you can also try to prove this one for us and try to tell us next time something like this, like you also know uh, maybe R3, and then uh, this determinant becomes like this if it's correct, right? That is this correct? Yeah, determinant splits like this, right? You must have learned this.
Mm,
R1 plus R2, then you can split the determinant like this.
you can.
Yeah, you can, right? This can you prove this using areas? That area also behaves like this. Okay.
Okay.
Right. So these two, I mean, those two. This is actually a generalization of that, but you can just present. It will be interesting present, geometry explanation of this. Okay, and this will again be useful to you later when you study generalizations of determinants, which are called exterior products and so on. So even determinants you will have to learn for some determinants. Even there are many interesting things which you will learn. So uh,
Yes.
yes. So
So,
that
but
is yes.
I have one question. Like, do you actually use the direction notion of vector ever?
Direction notion meaning.
I mean, we are here like in physics. We obviously have like direction is very important, right? Everywhere.
Mhm.
But
Yes.
in maths, like when do we use this notion of direction?
But vector has a direction naturally, right? Otherwise, if
That
there
is,
was no
that
direction, we
is,
will not talk about a vector. We'll just talk about length.
but yeah, that is true. That vector has a direction, but
We use directions all the time. Or you saying orientation?
like for example, like area vector also has a direction, right? It
Hmm.
has a convention of that curling the fingers and then
Yes, yes. Yeah, we
oh,
use that. Yeah, we use that distinction when the direction is positive, when the direction is negative.
okay,
Yeah, like the
okay.
sign of the thing, right? Yes. Yeah, you mean sort
Yes.
of orientation. Yeah, that is useful. That is very important.
But where do you use it?
Okay, so where have I used it the last time?
Because even when I'm doing this linear algebra or wherever I'm seeing, uh, like linear algebra is basically about linear transformation, right?
Hmm.
More than matrices, it's all about study of linear transformations.
Yes.
And
Yeah.
we said, but I have like while reading this book, I have like uh, there is not much emphasis on the direction of the vector. Like, but in physics, when you are studying the vectors, when initially they teach you vectors, they're all about the direction sense, like where is it pointing and how is it looking and so on and so forth. Like,
Yes,
that way,
because
that's why.
because I think that here we are more interested in the mathematical properties of vectors and in what in what generality can we apply those properties,
Yeah.
right? Like can we apply the same like can the like vectors have these properties of basis and so on, what other objects have, like polynomials have, matrices have, right? So we are interested in that, and so maybe that's why it is not so clear the this right hand thumb rule and so on, it's useful or not, but it is useful in maths. For example, we define so that we say that a class of spaces is not orientable if certain kind of right hand thumb rule fails over there.
Okay.
So something, so we use it to define that certain spaces are in a way they are bad. For example, uh, I cannot say this very well, but you must have heard of the Mobius strip,
Yeah.
right? And you see the Mobius strip, when you try to make it, like how do you make it? You have the strip and then you turn one side, right? So you make a twist, right? You make a twist
Yes.
and then you join the two end side, right? You get a figure, right? Now I but now you see this figure has something strange in the sense it is non-orientable. Why? How am I saying that? So you keep a certain direction at a certain point on the strip and then go around on that surface and come back to that same point. You will see that your orientation would have changed.
Right.
Right, this kind of
Okay.
thing. Right, yeah. So then we say that this is a bad surface in that
So
sense.
basically, like in topology or something, or in those areas, maybe this thing is useful.
Yes, 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 yeah. Vector field, a vector field where every point on the space we assign a direction. Now this is modeling like wind flowing in a space and so on, right? And then we use those physical properties of the wind flowing and so on to know what could be true. And then we make our definitions so that those things that could be true do actually become true. Okay.
Right.
Uh, yeah, like when you integrate along a surface, sorry, when you integrate on a surface along a curve, okay, then the answer should be zero. And we make our definitions as such that they actually are zero. Now here, what does integration and so on mean? Those things have to be defined then. Yeah, so it is
Yeah.
it serves as a guiding principle at least to make definitions and to get that the results we are getting will actually be useful, because the results we are getting are violating certain physical rules, then they are not, then they will probably not be useful. Okay. So
Right.
yeah, that way I can say. And maybe one last thing which you can investigate in today's thing also is whether the third case, right, whether what was the third case.
O1 plus O3 is O2, like
Yes,
those.
yeah. So can you get O2 from O1 and O3?
No, no, absolutely not. I don't think so.
You think no? Okay. So try to prove then. Then you have to prove it. And this time we
I
maybe
think
huh?
I think O2 is the most powerful operation out of
Okay. Okay. So
all
let's
the.
see if your intuition is correct. Yeah. And here we also see one very interesting feature. So what we proved is kind of like uh, that O3 is in the span of O1 and O2.
Yeah.
In a very vague sense, right? Like you start with a matrix and what are all the matrices you can go to by
Like
using O1
like
and O2.
O3, like the O1 and O2 are like kind of the generator function of O3.
Yes, they kind of generate, right? But then, unlike what happens in linear algebra, it doesn't happen here that using O1 and O3 you can get O2.
Yeah.
You see my point, right?
Mm.
Like, yeah,
Yeah.
the span, the reversibility is not happening. Okay, like V3 is in the span of V1 and V2. That does not imply that V2 is in the span of V1 and V3, which happens in
Right.
linear algebra. And you see, that thing that happens in linear algebra is the key to getting all the other results.
Okay.
If you notice it, right, that all the bases have same size, and from anywhere, any linearly independent set, you can get a basis. If you've not read it, maybe you will read it later. All these things, this reversibility is the key, and this reversibility is not happening here. Okay, so later on when you study more linear algebra, which is called module theory, you will go to that will be that kind of linear algebra where this reversibility will not be there.
Okay.
Okay, yeah, there
Okay.
basically. So why is the reversibility there in linear algebra? Again, that like that V3 is in the span of V1 and V2, then V2 is in the span of V1 and V3. What leads to the reversibility? It is the reversibility in the field. It is the multiplicative inverse.
Mm-hmm.
Right. And that's the thing. And so when you try to generalize linear algebra to, if you replace the field by another kind of mathematical structure, which is like a field, but everything doesn't have an inverse. Like
Okay.
Z6, integers modulo 6. You can
Yeah.
multiply, you can add, some things have an inverse, 5 has an inverse as 5
Like
itself.
the co-prime integers with 6 have an inverse and the one which are not.
Others don't have.
Don't.
So it's a pseudo field. So when you try to do linear algebra over that, then things become non-trivial, because then this
Okay.
reversibility is not there. Okay, then
Okay.
it will become interesting. Okay.
So for the next week, like, can we like solve some problems from Rudin?
Yes. Any chapter, which chapter are you
That
looking
too
at?
also. So point set topology, the second chapter, those problems.
Yes, yes. Yeah, anything. Yes, yes, that will be good for me. Yeah.
covering theorem because Rasuro is I guess also doing that because
Uh-huh.
now we are doing those compactness and complete metric spaces, all those things. So
Yes, yes, yeah, that will be good. I'll also get to revise these things. Yes.
so
Okay.
maybe 1 week we can do linear and 1 week we can do analysis. So
That will be fine. Yes. Okay, so let's pick where we'll you try as much as
one
you can and then we can
and
see.
one more thing, sir.
Yes.
Uh, sir, for what is the difference between this integrated PhD and masters?
Yes, I got to know of that difference in the hard way. Yes, in the integrated PhD, the one thing is that you cannot leave, right? If you leave, then you don't get the degree. That's how it is in most places. Okay.
Okay.
So yeah, and it will be a 7 years program. First 2 years will
I
be like
thought
a
that
master's.
it will be 6 years program, right?
I think the
Because
PhD
they
is
have
6 years. PhD is usually 6 years. Yes, maybe it will be 6 or 7 years, I
but
think.
like
Yeah.
you told us right that you have got into some integrated PhD program.
In IMSC. Yes. Yeah. So
And so is that good? Like
good in the sense that first of all it depends on your area of interest, but I think that's a slightly secondary point unless if someone is very advanced and they already have a clear area of interest. The good, yeah, it is very very good. So in India it is probably the best, like Institute of Mathematical Science is the best, but the slight downside is that if you feel that you can get a better place after masters, okay, then you will
okay.
feel that you are stuck. Now better is a relative term. Yeah, that
Uh-huh.
is that
Okay.
is the thing. And in the first two, then another point which is probably a little secondary is that in the first 2 years you get paid a little less.
Okay.
You get like I think 20K, and in a PhD you would get 35 or something. uh,
Okay. Okay.
yeah, so like it's like the first 2 years that you're treated as a master student.
Like but after this MMath you are like applying for again PhD, right?
Yes, I'll have to again apply for a direct PhD. Yeah, this time I will apply for a direct PhD. So what I felt is that, what I felt is that I could do better because I did not prepare for these exams and I still easily sort of still could clear them. So I felt that
No, but
maybe
I
I,
am just asking because some person told like I thought that the normal the integrated PhD has got less value than PhD because you didn't
no, no,
pursue it.
no, 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 no. I also got PhD in either Pune. I did not join. That was a direct PhD. Yeah.
Okay.
Yeah.
Okay.
The reason I did not get PhD in IMSC, the reason was that IMSC has the old rule which they have not changed yet, is that if you are doing your masters in a different subject, then you cannot do a PhD in a different subject.
Okay.
Understand?
Okay.
And either Pune happens to have changed that rule. It's a more forward institute, right? Uh, not that IMSC is bad. IMSC is probably better than either Pune, but in the sense of, yeah, IMSC is a little
Rules.
slow to change its rules. Yes. Yeah, I was getting either Pune PhD, but then again, either Pune PhD is very, very good. But I still feel that I can get slightly better. But I don't know. And maybe I also wanted a better foundation. So there are many topics which I don't know very well. So maybe I could learn
But
them.
then like IMSC, you are saying you are claiming is one of the best in India for
It is,
PhD.
it is, it is. Yes, it's certainly. If you are going
But
to work,
other than that, like, what is there? Like I think IIC is good, right?
yeah, it depends on your subject areas. ISC is good in geometry, IMAC is good in representation theory and number theory, TIFL is good in algebraic geometry. It depends on the subject. Yeah. ISI is good in analysis, best in analysis and probability. It's that kind of thing. It
Okay.
depends on the area. Yeah. Okay. Yeah. Okay.
All right.
All right. Okay.
Yes.
Okay.
Thank you.
Thank you. Bye.